Hello again. Welcome to part 2 of my mathematical challenge. My challenge is to consider dropping infinity from mathematics, getting rid of it altogether. And in part 1 I explained this as a 3-part challenge. First is if you don't agree that's a good idea, then your challenge is to tell me why. If you do agree, then there are 2 remaining parts. One is to put mathematics on a rigorous foundation, and that's what this part will deal with. And then the third part is to develop the calculus on this new mathematics that doesn't have infinity. That'll be the third part. Now, what I propose is accepting the obvious consequence. If you don't allow infinity, then the obvious consequence is that there would be some largest integer. And so I think mathematics should be built around the premise that there is a largest integer, and for this video series we'll call it m. So we have a mathematics that's that only contains the integers from -m to +m, and therefore it's discrete. That is, that we only have a finite number of integers. Now we have other discrete mathematics, mathematical systems that have been developed. For example, group theory. There are both finite and infinite groups, and it turns out the finite groups are the more complicated. And we have rings and fields that may be finite or discrete. But my system, that is trying to get a calculus using finite numbers, is different from those other discrete systems in that it's not closed, or can't be closed, under the operations of addition, multiplication, subtraction, and division. That is, in the other discrete systems, group theory for example, if you take any 2 group members and add them together, or multiply them, whatever the group operation is, you get another element of the group. You always get another element of the group. You must. Otherwise the set is not a group. In my system, which I call practical numbers, that's not the case. There are pairs of numbers that you can't add. You can't add all pairs of numbers. You can't multiply all pairs of numbers, or subtract all pairs of numbers, or divide them. Now, this really is not different from Orthodox mathematics in principle, because in Orthodox mathematics we also have similar omissions of definition. That is, we have pairs of numbers that you can't operate on using some operations. And the glaring example is you can't divide by 0 in Orthodox mathematics. Now let's just examine that fact. It's well known that you can't divide by 0 in mathematics, so the naive question would be, well, why not? How about, why don't we just divide by 0? How about, for example, I divide 5 by 0? Why can't I? And you say, well, because it's not defined. It's not prohibited. I mean, it's not permitted. And I say, well, what if we go ahead and do it anyway? Well, the fact is, if you try to do it anyway, you end up with inconsistent consequences. That is, if you make any sort of definition whatsoever for the term 5 divided by 0, you can prove from then on that 1 equals 2, or other inconsistencies. So any definition leads to nonsense, and that's why we can't define division by 0. So it seems like a reasonable prohibition, and in fact it is. And in my practical number system, it's no different. There are pairs of numbers which that are not defined and cannot be defined. And so it's no problem. We just omit those from our computations. But in practical numbers, there are pairs of numbers that you can't add, and that you can't multiply, and that you can't subtract, in addition to those that you can't divide. And so that might seem worse, might seem like, oh, that's awful that you can't add numbers and so on. But I might point out that in practical numbers, there are only a finite number of numbers, and so there are only a finite number of these pairs that you can't operate on. Whereas in Orthodox mathematics, there are an infinite number of numbers which can't be divided by 0. So there are more prohibitions in Orthodox mathematics than there would be in practical number mathematics. Not that that's important, it's just a curious fact. So now the question is, what are the prohibitions against adding numbers, or what are the limitations on the definition of addition? And we can look at that schematically. If you think of the numbers we have to deal with in practical numbers as ranging from -m to +m, and you lay those out on a number line, and then you take two of those number lines and make a Cartesian coordinate system. So you have an an x-axis that has all the numbers defined from -m to +m. And then you have a y-axis with the same set of numbers, all that are defined from -m to +m. And then every point on the plane is a pair of numbers, x, y. So for any point on the plane, x, y, we can ask the question, is the sum x plus y defined? And it turns out on this diagram, all those inside the rhombus, the answer is yes, they are defined. Actually, it's a little more than that. It's also some numbers up in this corner and down in this corner. But if we ask the question, for what pairs of numbers are the sum defined and also the difference defined, then we get inside this rhombus. So inside this rhombus, any pair of numbers, x, y, both x plus y and x minus y are defined. And so it's roughly half of the pairs that are defined. And so that seems like a severe limitation. But I think we'll show later where it's not. The idea is to choose m so big that for all practical purposes, the numbers we use are closer to 0, and therefore the sums and differences are defined. Similarly, if we ask, well, what products are defined, what we end up with is the pairs of numbers on the same xy plane that are inside of these hyperbolae. They're the ones that, if you multiply any numbers inside the envelope of those hyperbolae, you will get a number less than m. That is, between -m and +m. Any number, or any pair of numbers that's outside of that envelope, you'll get a number that doesn't work. It either goes, or the absolute value will be greater than m. So this is a more severe limitation because we have to now work within this inside. But again, if we choose m suitably large, then we'll have a range of numbers that will be practically useful. Okay, so that's the limitation on operations, addition and multiplication, actually addition, subtraction, and multiplication. The limitation on division, you can work out the same kind of diagram, and what you get is, instead of the single vertical line that we have in Orthodox mathematics, that is, every y value is excluded from the quotient x over y, in practical mathematics, practical numbers, you'd have a skinny little wedge that includes that y-axis, rather than just the y-axis. So now the question is, how do we fix up mathematics? That is, how do we put mathematics on a sound foundation so that we have just the practical numbers to work with? And the answer, I believe, is what's called Constructivism. That is, one of the principles that you adopt is that you don't deal with any concepts that you can't explicitly construct. And so what that rules out is concepts like induction, where you assume that you can continue some particular argument or definition or process ad infinitum. And that's even Peano's axioms that were used early on to provide a basis for arithmetic. There was the notion of the successor to a number, and the accepted belief was that you could continue to define successors ad infinitum in order to produce an infinite set of integers. And that we're not going to allow, because Constructivism would say I have to explicitly construct every number that I want to use, and so I have to explicitly define it. Now, we don't expect anybody to sit and write out all these numbers. We can use mechanical aids, and that's the way we should think about it, is what can we build into machines, because after all, that's what we use nowadays to do our calculations when they get to be significant. And the calculator machines are of various different kinds. And think about it as an abacus, for example. Here's a way to design and build a machine that can be used to help in computation. And let's say we build an abacus with 25 wires, like I mentioned before. We have now implicitly defined all the numbers from 0 to 10 to the 25th. And we can rigorously define what we mean by any particular number being represented by the beads on that abacus from 0 to 10 to the 25th. Even though the number 10 to the 25th is so huge that it would be impossible to write out all the numbers, to define them all individually, or even to list them. There's not enough material in the universe to list all the numbers that would go from 0 to 10 to the 25th. But we can agree that it makes sense to say that we have defined all the numbers from 0 to 10 to the 25th on that abacus. And similarly in our computers, we can define numbers by designing machines that have algorithms that can add, subtract, multiply, and divide numbers of a certain size. That is, a certain bit length to the numbers. Always limited by some maximum that we can identify or not. So now the question is, how do we deal with this axiomatically? And I'm not an expert. I'm not an expert in foundations, and so I can only make a suggestion that I believe is correct, and your challenge is to accept that or not and proceed with or without it. My suggestion is that we drop the axiom of choice from the commonly accepted ZFC axiom system that's accepted in Orthodox mathematics. That's the Zermelo-Fraenkel axiom of choice set of axioms that has been used to undergird all of mathematics, all of the definitions in all the fields of mathematics beyond set theory. Now, the axiom of choice is like induction. That is, it's an axiom that declares that it's okay to accept the notion of selecting elements from an infinite set, for example. And so implicit in the axiom is the acceptance of infinite sets. And that's precisely what we want to deny and exclude from mathematics. So if that makes sense to you, and you are a foundations person, or a young person that wants to get into the foundations of mathematics, think that over and explore it, and maybe it'll work. I think it will, and that's kind of up to you to take the challenge and decide whether or not it will work. So I'll leave it there. You can take it from here, and you can also consider part 3 if you're more interested in that, and that is my next video. And there we'll deal with the question of how would we define and then develop the proofs of what it takes to do calculus using practical numbers. And so I look forward to talking with you in part 3, and I hope you take up the challenge and leave me comments telling me whether you agree or disagree and what your ideas are. And so again, thank you for watching.